Right, so that's different. So CalDay is a purely voluntary thing. So if you would be about a month into your project at that point in time, I think. And in the past, what's happened is some teams have already had something to demo. So they've actually gone ahead and demoed what they have on CalDay. So you're welcome to do a demo on CalDay, and those will be recorded and typically put up, and it's a nice advertisement for your project as well as for the class. Other questions? Okay, so let's restart where Edward left off last time. Last Thursday, the topic was interfacing to sensors and actuators. And at the end of the lecture, Edward talked about two ways in which you could do this. So the first is called polling. And polling is a mechanism where you have a loop where you're waiting for the I/O device, checking periodically. And typically some kind of a flag is set in a register. And when that's set, you know the device is ready, and you go ahead and read a sample. Okay, so that's the polling technique. Today we'll talk about interrupts. Interrupts are a mechanism for an asynchronous mechanism for the I/O device to let you know when it's ready. So typically, there's some kind of external hardware that may raise a voltage on a pin that lets the processor know that an interrupt has been raised. The processor then stops what it's doing, suspends what it's doing, and it has to run code that will deal with the interrupt. And that code is called an interrupt service routine. Okay? So the processor invokes an interrupt service routine, and the ISR, or the interrupt service routine, runs. It deals with the interrupt and returns back to where the code had been suspended. Okay? So that's the overall mechanism. You've already, I think, in last week's lab, used interrupts, right? So you have some familiarity with what is involved in programming with interrupts. The goal of today's lecture is to tell you a little bit more in detail about what happens when an interrupt is raised, and more importantly, for you to be aware of the issues you need to think about when programming with interrupts. Okay? So those are the two goals of today's lecture. Yes, question?
Why do you say the ISR interacts concurrently?
We'll get to that. So, but the short answer, so the question is why, as on this slide, why is it that we say that the ISR interacts concurrently with the program? And really, the reason is that in logical terms, or just conceptually, the ISR and the main function are running concurrently. And the ISR can happen pretty much, an interrupt can be raised pretty much any time when the main program is running. Okay? But we'll revisit this notion of concurrency at the end of the lecture and talk about the difference between concurrency and parallelism, for example. What's your name, by the way? Karthik. Okay.
Stop me if you're going to cover this later in the lecture, but so in last lecture we discussed that there are trade-offs to using interrupts versus polling mechanisms.
Uh-huh.
Versus, for instance, there's a context switch overhead during converting to an interrupt because you need. But it seems to me that the context switch overhead for an interrupt service routine, most of it, because most of them don't run operating systems.
Right.
And so you wouldn't have to switch out virtual memory or agent something, and that's where most not safe registers. And so, is there any way you can address that?
Okay, sure. So that's a good question. What's your name?
Ryan.
So the question is, what are the trade-offs between polling, interfacing using polling and interfacing using interrupts? I think this is an issue that Edward addressed at the end of last time's lecture. But very briefly, so the question was, is the context switch overhead of servicing an interrupt a significant issue? And in most cases, it's not. Okay, so it's not the context switch that makes programming with interrupts tricky or less desirable. What's more important is the fact that the interrupt service routine executes concurrently with the main program. And so you're really doing concurrent programming. And you have all the issues that come up when you do concurrent programming, right? Especially if there are shared variables between the ISR and the main routine. And this is something that we will discuss in depth later in this lecture. So that's the main issue. With polling, of course, the issue is that your processor is tied up just doing a busy wait on the I/O device, right? So that's the downside of polling. But it's safer in the sense that there is no concurrent routine running with the main program. Okay. Okay. So, so very briefly, this diagram shows you how interrupt service routines operate. So the way it works is initially, before the main program executes, you have an idea of what interrupts you expect to be servicing when the main program is executing. And so you typically run some setup code where you, for example, register the interrupt service routine. So you say, when this interrupt is raised, this is the code that has to be executed, right? And then you go ahead and run whatever the main function is, right? So the processor is executing its task. And at some point, an interrupt occurs. Okay, when an interrupt occurs, the processor executes a context switch, meaning that it stops, it suspends what it's doing, and it goes and runs the interrupt service routine. And when the interrupt service routine finishes, it goes back to where the processor left off in the main program, and that resumes. Okay, so that's the mechanism. So in a little bit more detail, there are, broadly speaking, two kinds of interrupts. The first is a hardware interrupt, which is implemented typically by the change in a voltage level on a pin. Okay, and the processor then responds to that change in voltage level. It knows what interrupt was raised. Typically, it might check a register to know what interrupt was raised, and then it deals with that interrupt. The other way you can have an interrupt is through a software mechanisms. So, for example, what could happen is that a special instruction could be executed, and that triggers an interrupt, or there is a write to a memory map register which triggers an interrupt. Okay, so both of these mechanisms trigger interrupts, and you typically deal with them in the same way. So the response in doing a context switch to an interrupt service routine is that you first disable interrupts. Okay, so when you execute an interrupt service routine, typically unless there are other interrupts that have higher priority, right? You disable interrupts so that you're able to execute the interrupt service routine to completion before you return. Yes?
Is like Stack Overflow or the divide by zero stuff, are those like software interrupts or they're like different?
So the question is a Stack Overflow or divide by zero a software interrupt? Those are typically, so divide by zero is typically a hardware level mechanism, right? A Stack Overflow is, I think it can also be implemented using a hardware level mechanism. So a software interrupt, an example of a software interrupt, for example, is, let's say, you can have an exception, right, which is raised when a code is running, and that exception could be implemented using a software interrupt mechanism. Okay, so when a context switch happens for an interrupt, you typically disable interrupts first, and then since the interrupt service routine itself is executing code, it might it's certainly going to increment the program counter, and it might use registers that were being used in the main program, right? And so what you have to do is similar to what you do when there's a procedure call. So you have to save the program counter, and you have to save perhaps the processor registers that the interrupt service routine might overwrite. Okay, so you save that state, and then the interrupt service routine typically jumps to a certain designated address. Okay, this designated address where the interrupt service routine, either the core of the interrupt service routine resides, so the processor then starts executing that code, or it can be a table of addresses of all the interrupt service routines. Okay, so up here is an example from the Atmega 168 processor that was discussed last week. This is the processor that we that we used the first time we taught this class. And what you're seeing here is really the interrupt, what's called the interrupt vector table. So it's a table which has one instruction, one jump instruction for every kind of interrupt. Okay? The address in this table, for example, if you look at this address, this is for the reset interrupt, and the address itself is known as the interrupt vector. Okay? So so typically, when the interrupt occurs, you jump to the interrupt vector, which could be the start of the code, or in this case, it's a row of the interrupt vector table. And this is essentially a region of program memory. So on the Atmega 168 board, this is the program memory resides in flash, right, as you saw last week. And so the processor jumps here, and then this instruction, this jump instruction, then tells it the target of this jump instruction is going to be the code for the corresponding interrupt. So for the reset, it'll jump to a segment of memory, which will then deal with the reset signal. If you have a timer interrupt, then you'll jump to a section of memory which deals with the timer interrupt. Okay? So all this happens before the ISR starts running. Then the ISR code is executed. And then at the end of the ISR, it has to it has to restore the values of any registers that it had saved before running. So the ISR then restores any registers it uses, and it re-enables interrupts, and then returns back to the main function. Okay? So that's the overall flow of what happens when an ISR is raised, when an interrupt is raised. Okay. Now, oftentimes it's useful to raise an interrupt after a certain amount of time has elapsed. Okay, so for example, you might be sampling a sensor at a periodic interval, let's say 1 millisecond, and every time 1 millisecond elapsed since the last sample you took, you want the interrupt to be raised so that the main thread then goes and gets the new sample, right? And so this is a very common mechanism that's employed, the timed interrupt. So here the diagram is similar to what we saw earlier, in that you do some setup code and you have to register the interrupt service routine. But you also have to initialize the timer, right? So the timer is initialized to some value, and it starts counting down from that value. And when it reaches 0, then it triggers an interrupt. So what you have to do is initialize the timer to the high value that it starts counting down from. Okay? And then when the timer expires, an interrupt is raised, and the task that you're running now gets interrupted in the same way as we had in the previous case, where you had an asynchronous interrupt. The processor then jumps to the ISR, and the ISR runs, and you might get a new sample, and this code that might also go back and then reset the timer back to the high value so that again it starts counting down, and the process repeats. Okay? So the timed interrupt is a fairly common mechanism used to get periodic samples of sensor data. Okay, so let's take a look at two ways of implementing the timer interrupt. So the first example is setting up a timed interrupt on the Atmega 168 to trigger an interrupt every 1 millisecond. Now, we'll see an example of how to do this on the Atmega 168, and then we'll see another example of how to do it on the Luminary Micro. Every microcontroller board is different, and so you have to go back and read the manual and see how to implement this. And also, you'll see there's quite a variation in the way to do this. So in the Atmega 168, what you do is you directly write to memory map registers. So you have a register, a pair of registers that are the timer control registers. And so you have two statements that you have to write to these registers, a particular mask value. And this essentially puts it in a mode where it's enabled to generate an interrupt whenever the timer counts down to 0. Okay? So, so effectively, you're enabling the timer here. The next write is to a register to tell you what the value is that it's going to start counting down from. Okay, so in order to figure out what's the right value, so here what we want is that the timer must expire every 1 millisecond, right? So in order to know what's the right value to count down from, you have to know what the clock frequency is, and then using that clock frequency, you then have to count and initialize the right value in the register so that when it hits 0, 1 millisecond has elapsed. So if you go back and read the manual, then you find out that for this processor, the clock frequency is 18.4832 megahertz. Okay, so we know the frequency, and then we also have to go back and look and see how often the timer is updated, right? Is it updated on every cycle, or is it updated on every 10th cycle, or what is it, right? And so if you go back and read in the manual, it says the timer runs at 1/256th the speed of the processor. Okay, so that tells you that you have to use this 256 factor in computing the right counter value to initialize the timer to. Okay, so the formula here is that the value of this register is going to be the processor frequency divided by this prescale value, the 256, times the interrupt frequency, how often you want the interrupt, which is going to be 1,000 hertz, right? 1 millisecond. So you want the interrupt to be generated at the rate of 1,000 hertz, and so you compute this value. It turns out to be 71, and so you initialize the register with 71. Okay. So now we've enabled the timer. We've written to the register the right countdown value, I'm sorry. You've put the timer in the mode in which it generates an interrupt, and then you've written the right value, and then finally you write into this mask register the right bit pattern that will enable the timer interrupt. Okay, so you do the sequence of writes to these memory map registers, and that sets up the timer interrupt for 1 millisecond on this processor.
In this kind of timers, like when it rolls over, does it have another interrupt to say like, oh, I rolled over?
Okay, that's an excellent question. Your name is Nima. Okay, so the question is, what happens when the register that's storing the count value rolls around, right? So a priori, there is no. So when it hits 0, it will raise an interrupt, right? And but there's nothing that stops the timer from keeping counting, right? So it will start recounting again. So what you have to do is when the interrupt is raised, you have to go back and reinitialize the right count so that it starts counting down again correctly. Okay, this is something to be aware of, right? So having these wraparound issues can actually cause you to interrupt less or more frequently than you want. So you have to be aware of this. Okay, Karthik? The timer is in hardware, that's right. That's right, yeah. Yes?
What kind of decisions will that make? For example, let's say the timer interrupts being raised. Does it remember which interrupts were raised, or how does it handle that?
Okay, so the question is, suppose multiple interrupts are raised, right? Then how do you remember that all these interrupts have been raised, right? Again, this depends on the hardware mechanism that's implemented. So if the interrupt, the way the interrupt is indicated is simply by raising a voltage level, you can only have essentially one interrupt pending at any given time, right? And until that interrupt is serviced, no other interrupt from the timer, for example, can be serviced, right? But it's possible also to not have simply a voltage level, but then have, let's say, a buffer of some kind. And then that buffer will buffer a certain number of interrupt requests. Okay, but I think on this processor and on the Luminary, I think it's just a voltage level. Okay, other questions? I didn't ask you for your name. Okay. Ian. Okay. All right. So that's the setup code on the Atmega 168. Yes.
So let's say I was in some other interrupt, like we had some other like controllers interrupt.
Mhm.
The timer interrupt occurs.
Okay.
You're gonna have something that indicates that the timer interrupt occurred while you were servicing one.
Okay. Excellent question. What's your name? Apurva. So the question is, what happens if you're servicing interrupt A and some other interrupt B occurs, right? Now, if you're servicing interrupt A and you've disabled all interrupts, then you will not be able to respond to interrupt B, right? But when you then re-enable interrupts and interrupt B is still active, you will be able to respond to it, okay? Now, it's also possible not to disable all interrupts, because clearly in some cases, there could be different signals that you can rate in increasing order, right? So maybe the reset interrupt is the most important. When you reset your robot, it has to stop, right? And you don't really care about the accelerometer sample, for example, right? So you might want the reset interrupt to have higher priority than the interrupt from the ADC. And so in that case, the priority has to be set, and you disable only the ADC interrupts when you go in to service it, okay? So you can have a priority between multiple interrupts. Okay, so this just repeats what we said. So what I showed you here is a snippet from the manual. But in C code, what you would do is in the main function, before you start executing the main code, you would execute all these instructions. And the way so for example, last time in class, we talked about not using the actual addresses of memory map registers, right? You typically want to use names like TCCR1A rather than an address 0x20, for instance. So these names are defined in a certain header file. So if you actually want to go and see what addresses these registers correspond to, you can go to this header file and have a look. Okay, so if you were to set up the interrupt hardware in C, you would include the register file and you would execute the setup code. Okay, so that's the way it's done in the Atmega 168, kind of low level. If you look at the Luminary, which is the board that we used in the past 2 years, and you say you want to do the same thing in the Luminary, right? So set up a timer to trigger an interrupt every 1 millisecond. Then the code involves these two functions. So it looks more like using a C API to do the same things that we had on the previous slide. So the first thing you do again is set the period of your timer. Okay, so this is doing what this line over here was doing, right? But it's doing it a little more elegantly, so easier for you. So you get, for example, here the number of cycles per second of the clock, right? And then you divide that by 1,000, and that gives you the number of cycles per millisecond, and that's when you want an interrupt generated. Okay, so you say this is going to be the period of my of the SysTick timer interrupt. Okay, so you set the period, and then you enable the timer to start counting, and then you enable the interrupt itself. Okay, the same three operations as we had in the previous slide, but a little more easier to do. When you are done, you disable both the interrupt as well as the timer. So the timer stops counting, and the interrupt also is disabled. Okay. So that's how you would do it in the Luminary. So now let's think about how you would use this. Okay. So we're now going to see how we can write a program, an interrupt-driven program, using the interrupt on the Luminary, the timer interrupt on the Luminary. So the goal here of the main routine down here is to run a certain code for 2 seconds and then stop. Okay, so the code you want to run is represented by this one line. Okay, but this could be an arbitrarily long sequence of code, right? So think of some C code sitting over here. It doesn't have to be one statement. It can be as long as you want. And what this while loop is really doing is it's busy waiting on the value of this variable timer count. It's waiting for timer count to count down from 2,000 to 0. And when it reaches 0, it's going to stop executing this code and reach the end of the function. Okay? So that's what the main function is doing. Yeah?
What happens if the code you're running took actually more than 2 seconds?
What happens if the code you're running is more than 2 seconds? Okay, excellent question. What's your name?
Dorian.
Dorian. Okay, so tell me what would happen. This code would not do what we're supposed to do, right? The specification says do something for 2 seconds and then stop. But if the code itself takes longer than 2 seconds to run, then clearly it's not going to satisfy the specification, right? How can you tell if the code is going to take more than 2 seconds? Yeah.
Check the value of the timer and see if it goes less than 0.
You can check the value of the timer. Okay, excellent. So we hope, assuming the timer here is implemented correctly, right, and it counts exactly 2 seconds, then when you finish running the code, you can check the timer value. But what if the timer wraps around and gives you some kind of a illegal value? Then what do you do? Yeah, Apurva? Okay, so the suggestion is to check the assembly code. So you compile this code, you look at the assembly, and you have a bunch of instructions, and you try to count. You say, okay, maybe every instruction has to take at least 1 cycle, right? And you count the number of instructions. Let's say if the count was, and then you multiplied by the appropriate second value, right? Let's say that was less than 2 seconds. Does it mean that it's actually going to be less than 2 seconds? You don't know. You don't really know, right? Because even if you look at an instruction manual, for embedded processors, it's easier than for general purpose processors. But the problem is an instruction may not take even one definitive cycle value, right? So loads and stores, for example, are one problematic case, especially in processors that have caches, right? So the number of cycles a load or a store might take can vary by an order of magnitude depending on whether you had a cache hit or a cache miss. Okay? So so the short answer to this question, this is actually a deep question that Dorian raised, right? How do you figure out how long a piece of code takes to run? This is a whole research area that people have been working on for 20 plus years. It's called execution time analysis, and it's a topic we will study in April. But for now, the thing to do is just let's assume that the code, the ... code here, takes less than 2 seconds. Okay, and let's go ahead. But that's a very important point that you raised. Okay. Question?
But what happens even if it's less than 2 seconds, if it's a significant fraction of 2 seconds?
Right.
So it doesn't work.
Yep.
Not exactly.
That's a problem. Yeah. Okay. All right. So, yeah.
You can probably go over those 2 seconds too, because any time in between goes on the interrupt, right?
Right.
And that'll take up some of your cycles.
Okay. All right. All excellent questions. So the reason we're going to go through this code for at least a few slides, or probably most of the rest of the lecture, is because there are a lot of issues that arise when you code with interrupts, right? And it gets really hard. And even this simple program will illustrate all of these points. And you guys have already raised one point, which is depending on how long that ... code takes, this mechanism might not actually work. It may not ensure that this does something for 2 seconds. Okay. But let's put that aside for a second, right? For several minutes, that issue, and let's think about this code. Let's say is 2 instructions or something really short. Okay. Now, would this do what it's supposed to do? Okay. So let me go through the rest of the code, and then we'll think about all these issues. Okay. So so timer count, right? That's the variable that we are setting to 2000 and then counting down from. That happens here. Before the timer count is initialized, we have the initialization code for the timer interrupt, right? The code that we had on the previous slide. And what you're doing here is so remember this function we had I see we don't have it here. Okay, so So this function here connects the timer interrupt to the interrupt service routine, right? So you've defined a function here, ISR. Okay. What you do is you have this ampersand ISR notation. Does anybody know what that means? The address of the function ISR. ISR. This ampersand ISR is a function pointer. It's a pointer to where ISR starts, the address. So you get the address of the ISR routine, and you register that as the ISR for the systic interrupt. Okay. So let's look at the ISR routine. Okay. So what it does is really simple. It checks if timer count is not equal to 0. And if it's non-zero, then it decrements it and returns. Okay, so that's what the ISR does. So let's look at this code, for example. So let's look at the timer count variable. It's a static variable. It's a global variable initialized to 0. It's an unsigned int. Okay, it's an unsigned int, and it also has this type qualifier or type modifier called volatile. Does anyone know what volatile means? Yeah?
Jacob, it signals to the compiler that it shouldn't optimize that variable, it could change it anytime.
Okay, good. So it signals to the compiler, the volatile type modifier signals to the compiler that the value of this variable could be changed anytime, not just in this function. And therefore, the compiler, for example, should not use a register to store the value of this variable. Instead, every time it sees this variable, an access to this variable, it has to go back to memory to read the value. And each time it writes to this variable, it has to go and update the value in memory. Okay? So that's what volatile tells the compiler. So, okay, so you have a static variable, you have the volatile keyword. Why do we have timer count defined as volatile in this code? Okay, so you have a write to timer count, a write and a read to timer count down here, and you also have write and read to timer count up here, right? And suppose timer count was stored in a register down here, then this code what would happen to it? Okay, so let's see. Suppose timer count was stored in the register here. Then what happens is the register is initialized to 2000, and every time you run this code, you're going to be checking the value of this register. Okay, you're going to be branching on the value of that register. Well, that register is set to 2000, and this code is not writing to it after that. So it's just going to stay at 2000, right? And so this code is going to run forever. You'll have an infinite loop in your main function. While even if the ISR was actually updating the value of timer count, the main function would never see that. Okay? So this is already pointing to the kinds of issues you have in concurrency. Here in this code, timer count is intended to be a shared variable between these two functions. And you have to ensure that when the ISR updates the value of this shared variable, the main function is able to read it. Okay. Yes, Dorian. Why it's not decrementing it? Yeah, so let me repeat what I said. So suppose we do not use the volatile keyword, right? Then in compiling this code, the compiler could very well allocate a register to store the value of timer count. So what the compiler could do is say that while I'm executing this code, I'll just use a register to store 2000, and then every time I run this code, I will check the value of the register, right? That's faster than going to memory, right? And run this code, and then eventually the timer count variable can be updated if it's used later, but but it doesn't have to be updated here because this code only depends on the value of timer count. It's okay to show that value in the register, right? And so that was the point that I was trying to make. Okay, using the volatile keyword, you ensure that the value 2000 is actually stored to the memory location where allocated to the variable timer count. And each time you run this while loop, you check the value of that variable. Okay, so now the point here is that the ISR code and the main code are really running concurrently. Okay, and in this case, what that means is that between any two machine instructions of the main code, an interrupt can happen and the ISR can be executed, right? And likewise, even running this ISR, if you don't disable interrupts between any two machine instructions of the ISR, there can be an interrupt that can suspend the ISR and then trigger some other code to run. Okay, so what you have to do when you write code like this is reason about what happens essentially between any two machine instructions of the code. Okay, and think about all those possibilities and whether there exists some such case where an interrupt happens between two machine instructions that breaks your code. Okay, that's one of the things that makes it hard to program with interrupts. Okay, so let's think about what happens when the interrupt happens. It occurs at various places in the code. So let's say the interrupt occurs right here before you execute timer count equals 2000. Okay, so what would happen? Okay, so one of you, Bailey.
You would probably work okay.
It would work okay, meaning what would happen to the value of timer count? It should stay at 0, right? So timer count is initialized to 0, and let's say it's not updated anywhere here. So the first write to timer count occurs here when it's set to 2000, or if the ISR, if this statement was executed, right? But we see here that the timer count minus minus, the decrement is executed only if timer count is not equal to 0, right? And so we initialize timer count to be 0. Therefore, this conditional will never be true. The decrement won't be executed. And so if an interrupt happened before we set timer count to 2000, then timer count stays at 0. Okay? So so we haven't really started decrementing it yet. Okay. So what happens if the interrupt occurs right after the write to timer count? So I set timer count to 2000, and then the interrupt happened. You start losing time. Okay, so certainly an interrupt has happened, so 1 millisecond has elapsed, right? So we're already counting down, right? But what else could happen? Yeah? When you're processing the interrupt, the timer is still counting down, but the implementation here, so you have to go back and look at the manual. The implementation would reset the timer back to the high count value so that, again, it starts counting down to 1 millisecond. Right? Okay. All right. So okay. So let me repeat what Apurva said. So at the end. So the question, the point that was raised was, what if the ISR routine takes, of the order of 2 seconds to run? Okay. So you have a big ISR routine. Then the ISR, if we disable interrupts at the beginning of the ISR, right, and we're running the ISR itself, there could very well be other timer interrupts that are raised when the timer expires, but the interrupts are disabled, so the code will not react to them. So in fact, 2 seconds could elapse, and you would have only decremented timer count once. Okay, so that's a problem. So having a large piece of code in the ISR can be a big issue. In fact, some of you might have experienced this in the lab already, right? So we all like to debug using printfs, right? And when you debug code that is interrupt driven, you have to be really, really careful not to put printfs in the ISR, right? Because bad things will happen. So so typically the rule of thumb is keep the ISR short as possible. Okay. All right. So, but getting back to this question, if the interrupt happens here after timer count is set to 2000, then the ISR executes. Timer count is non-zero, so it decrements timer count. Okay. So at this point in the code, what we know is timer count is going to be less than 2000. Right? It could be decremented once, but it could also be decremented multiple times. We expect that after the timer count equals 2000 instruction is executed, the branch corresponding to the while statement here should execute shortly thereafter. So we don't expect that to take 1 millisecond, right, or a few milliseconds. But there is nothing in the specification of this microcontroller board that disallows that. So it could well be that some other interrupt occurred there, and that ISR started running, okay, and therefore you didn't execute this branch. Then the timer interrupt happened again, and you decremented the counter twice. That can well happen, okay. So so it's not just that one interrupt can happen here; multiple interrupts could happen. Okay. What about if the interrupt happens inside the loop? That's the expected case, right? So you expect the interrupt to happen inside the loop, and then you decrement timer count, and when timer count reaches 0, then you're happy. But you have all the same issues here that you had right after the timer count equals 2000 statement. So the interrupt can happen multiple times, and none of this code might have made progress. Okay. All right. Now it's possible. We already talked about this. The interrupt can happen twice or multiple times during the execution of the code. Okay. Now let's think about what happens if an interrupt occurs inside the ISR. Okay. So what if you get a second timer interrupt? Well, first of all, the question is, can you get a second timer interrupt at the end of this conditional? Okay. And the second question is, if yes, what happens? Okay. Yeah. You can get it as soon as you re-enable interrupts. Okay. But you have to read the documentation to know if this the setup code for the ISR automatically disables and enables interrupts. Okay, it's not the case for all platforms that you would have the setup code do that automatically, but turns out for the Luminary it does it. Okay, so when the ISR, if you look at the instructions that correspond to the interrupt the setup code that is jump to, right? So you had this jump table, and if you get the systic interrupt, you jump to a piece of code that does the setup in this case. Okay, so it disables interrupts at the beginning and it re-enables interrupts at the end. Okay, and it does that using machine instructions. All right. So the setup code for this ISR already does that. But Karthik has raised a different question. Okay, he says, okay, what happens if interrupts were re-enabled, but before the ISR returned, another interrupt happens? Okay, that's entirely possible. It's improbable, but it's possible. Okay, so you run this ISR, you re-enable interrupts, and then just at that point, when you re-enabled interrupts, another interrupt happens. Well, then what will happen is you'll go back and re-execute the ISR. Okay, run the ISR again, and it's possible that again at the same point where the interrupt was re-enabled, boom, you have another interrupt happen. Okay, so what can happen here is you can get an infinite chain of interrupts. Okay, on each interrupt call, you will decrement timer count, right? So timer count can reach 0, And that could happen potentially even before you even started executing this code, right? So timer count reaches 0 already, you quit, you haven't run the code at all, right? And 2 seconds have elapsed. Okay, now this goes back to a point that was raised earlier, which is what happens if the interrupt service routine is long, right? It takes a while to run. Okay, so the reason we think it may not happen in this code is because the interrupt service routine is short, right? So you don't expect another millisecond to elapse between when the code starts executing and when it ends and re-enables interrupts. Okay, but if your interrupt service routine was long, then it's entirely possible for you to get another interrupt just when you re-enable interrupts here. Yes? Yeah.
What do you mean exactly by main and ISR concurrently?
Okay. So so the question is what is meant by the main and ISR running concurrently, right? And so in the context of this code, what that means is that between any two instructions of the main routine, the ISR can execute, right? So it's not that the main routine executes to completion before the ISR runs. Okay, that would be sequential code. So in sequential code, when you run a piece of code, you expect it to run to completion. Okay, but here what happens is between any two instructions of your main function, you could then have the ISR execute, and possibly between two instructions of the right two instructions of the ISR, you can have another instance of the ISR execute, and so on, right? And so exactly. So it's a form of interleaving, right? You take the code of the ISR and really you run a piece of the main function, then you run a piece of the ISR, and then you run the remainder of the main function. Okay, and so the code for the ISR is interleaved in between the code for the main function. Yes, question?
Also in this program, once it gets into the while loop will be finished, right? No matter how many interrupts occur.
Okay, that's a good question. So in this while loop, right? The question is, what's your name, by the way? Pranav. Okay, so the question is, really, will this while loop terminate, right?
No, once it is inside, it will definitely finish, right? No matter how many interrupts.
Once it is inside, will it definitely finish? Okay, so this is probably what I'm going to talk about next. So hold your question, and we'll think about this. Okay, so let me just label the code here with program locations. Okay, so A, for example, is the program location right after timer count equals 2000. B is the program counter location right before this code is executed. And C is the location at the end of the main function. Okay, so Pranav's question is, suppose you were at B or somewhere in between here. Is it guaranteed that you'll eventually reach C, right? If the while loop terminates and then you quit, correct? Right. So think about this. Okay. So the question is, I think I have it here. Assuming that you can get interrupts. Interrupts are enabled infinitely often, meaning it's possible to get an infinite sequence of interrupts. Okay, is it guaranteed that the program location C is always reached, meaning that the while loop finishes? Did I see a hand up here? Okay, yes, Ted. Okay, all right. So good. So so this goes back to the observation we made a few minutes ago, which is it's improbable but possible for you to have the ISR interrupted right at the end when interrupts are re-enabled, okay, and a new instance of the ISR runs. That could very well happen when the main function is in the middle of this code, right? So you could end up having this infinite chain of interrupt service routines running, okay, and the code would never get to location C. Okay, so it's unlikely, but there is a possibility of that happening. Okay. Yes.
In this particular architecture, when an interrupt happens, does it immediately handle it, or does it wait for your instruction to finish and then handle the interrupt?
So the question is, in this architecture, when an interrupt occurs, does it wait for the current instruction to finish execution and then services the interrupt, or does the current instruction get quashed, basically? Right? This is so. The question, I don't really know. You have to go to the ARM manual. So this processor uses a version of the ARM7. So you have to go to the ARM manual and see. Suppose there's an instruction that's in the pipeline executing, and an interrupt happens. What happens to the instructions in the pipeline? Right? Do they all get quashed, basically, and nothing happens, and you just have bubbles in the pipeline, or do all the instructions in the pipeline complete and then the interrupt is serviced? So I don't know, but we'll have to go to the processor manual and check that out. Okay. Other questions? What's your name, by the way?
Bert.
Bert. Okay. Okay. So suppose we had this code. Suppose we are stuck with this code. Then what are the assumptions we need to make, or what are the assumptions under which this code will work? Okay, question? You're not infinitely interrupting. So ideally, you want interrupts to be able to happen infinitely often, right? Because in an embedded system, you intend the system to run forever, right? And interrupts are, the reason you're using interrupts is it's generating some useful sensor data or something like that. So you don't want it to happen that after a certain amount of time, after 2 hours, you don't get any more interrupts, right? That would be bad. But what shouldn't happen is the situation we discussed, which is the case where you run the ISR and then you get interrupted, and then you run another instance of the ISR and get interrupted again. Okay, that should not happen. So under what conditions would that be highly unlikely to happen?
The time you're predicting the ISR to take is much shorter than the period of the interrupt.
Okay, so if the time that the ISR takes to execute is much, much shorter than the time between interrupts, right? Then if you let's say we're able to prove that the time that the ISR takes is much less, right, than the time between interrupts, okay? Or more precisely, it's strictly less than the time it takes to set up the code, time it takes to run this code, and time it takes to run the restore code, right? If the time between interrupts is greater than that amount of time, then we are guaranteed that this ISR cannot get interrupted by itself. Okay? So that's one assumption. It's an assumption on the amount of time this code takes. Okay? So that goes back to the problem of execution time analysis. Okay, but let's say we make that assumption. What else? Do we need any other assumptions about the main function? Yes, Ted? In the while loop, you don't mess with the timer count. Okay, yes. So let's assume that this code that is being run does not write to timer count.
I guess it goes back to what Bert said. It depends on when you check. If the timer goes to 0 and the interrupt hasn't been fired yet, it's likely that it will come out of that.
Right. Okay. So it's so the situation that we have to consider, which we discussed at the beginning of the lecture, is the amount of time this piece of code takes, right, can impact whether this code works or not, right? So if this piece of code is short, right, like 1 or 2 instructions, then one could consider assume reasonably that okay, you check the value of timer count, you run this code, and another interrupt may not have happened. The time between, so let's say that an interrupt happened and timer count was decremented. From that decrement point, it would take several iterations of this loop before you reach the next decrement of the timer count. Okay, but it's very hard to get this exactly right because there is still a possibility that the last interrupt happens when you're just about to start executing the last iteration. So you actually hit the 2-second boundary, and but you have no way to stop this code. So you run the code to completion, and then you reach here, and then timer count is 0, and then you quit. But you've taken 2 seconds plus, a few microseconds, right? So that's entirely possible. So in applications like this, where you have to run a piece of code for a certain amount of time, you also have to account for tolerances around them. So typically, you design the code so that these tolerances are small, and then you account for the tolerance and the overall bound on the time taken by the main function. Okay, so those are the things to those are the assumptions on the time the ISR takes, on the time the code in the main function takes, and the assumption that the code in the main function does not mess with timer count when it's running this loop. Okay, so now let's get to the question that was raised at the beginning of the lecture, which is what is the difference between what is concurrency, and in particular we hear a lot about parallelism these days, right? So parallel computing is going to take over the world, and so there is a distinction that you need to understand between these two terms. Okay, concurrency and parallelism, they're two distinct things. So concurrency is a property of a program that holds if you have different parts of the program that conceptually or logically can execute at the same time. Okay, so if we go back to this code, the main function and the ISR conceptually can execute at the same time, meaning that if you're running the main function, it's possible at some time point, some arbitrary time point, for the function to get interrupted and the ISR to resume at that time point, right? The ISR to get started at that time point. Okay, so that's what we mean by saying that the main function and the interrupt service routine can execute concurrently. Okay, what's another example of concurrency that we all use regularly? Right? So we all use computers, a laptop like this, right? And there are two forms, at least, of concurrency that you can identify here. Yeah.
Every set of applications you run, like different applications, they use processors.
Okay, exactly. So processes, right? The different applications run as distinct processes. Sometimes an application runs as multiple processes also, right? And these processes run concurrently because the operating system scheduler can decide to run a little bit of this process and a little bit of process 2 and a little bit of process 3, and you can't tell at any given point of time which process is running because they all appear to be running at the same time, right? So that's logically executing simultaneously, which is concurrency. Another form of concurrency is threads. So even within a process, you can have multiple threads running, and we will discuss threads in a couple of weeks. So those of you who are not familiar with what threads are, don't worry, we will get to that, and you will get a chance, I think, to program with threads also. But that's another form of concurrency. So even within a single process, you can have multiple threads whose execution can be interleaved. You can run a little bit of thread 1, a little bit of thread 2, a little bit of thread 1, etc. Okay, so that's what concurrency is. Parallelism is slightly different. So in parallelism, you have physical simultaneity. Okay, so you can have a laptop with 2 cores, and you're running process 1 on core 1 and process 2 on core 2, and they're physically running at the same time. Okay, there's no interleaving going on. If you pick a point in real time, then process 1 will be running and process 2 will also be running. Okay, so you can see from this that parallelism is a case of concurrency. A parallel program is a concurrent program, but not all concurrent programs are parallel programs, right? And we've in fact, for so many years, we've had computers running on a single processor, but we've had the ability to do concurrent programming. Okay, so there's lots of different ways of implementing concurrency. We've seen handling interrupts. Processes is another one. Threads is the third. And then nowadays, multi-cores are everywhere. It's somewhat scary that they're even getting into safety-critical embedded platforms, right? So you have to be really, really careful when you program multi-cores in an embedded platform because everything gets so much harder, right? So predicting the amount of time a piece of code takes is really hard. It's actually an unsolved problem for concurrent programs, let alone multi-core programs. And so, so that's from the embedded perspective, you have to be extra careful when you code with multi-cores. But the fact is, multi-cores are here, and you have to learn how to program them. And that's yet another form of concurrency that you all will be soon familiar with. Okay, so so the summary here is recall that this lecture is about interrupts, and you will be using interrupts. You used it last week, and you will be using heavily in the next couple of weeks as you go through the CalClimber lab. The issue with interrupts is they introduce a great deal of non-determinism. I guess you've all been introduced to the concept of non-determinism, right, in the lecture on state machines, right? So, so non-determinism is a situation where you have two possibilities, and both of them could occur. Right? And in the case of interrupts, what this means is that if you go back to the example, then let's take the case where you can have an interrupt occur right at the end of the ISR where the interrupts are re-enabled. Okay, there's a possibility that you can get another interrupt at that point, or you don't get an interrupt and you can go and complete the ISR and return to the main function. Those are two possibilities, and without making any assumptions on the timing of the code, both possibilities can happen. Okay, so that's what we mean by non-determinism. Okay, there is basically you can model this as a state machine, and in that state machine you'd have a state which corresponds to the end of the ISR when interrupts are re-enabled, but before you've returned, right? You have that state, and from that state you have two edges, two transitions going out to two different states, okay? And you have non-determinism. So, so interrupts introduce non-determinism. All forms of concurrency introduce this kind of non-determinism, and you have to reason about the program really, really carefully, okay? So what we're going to do in the next 3 lectures, starting Thursday and then going into next week, is we'll go back to the material on state machines. Okay, so you've already seen in this lecture that even for a really simple program like this, there were all these issues that can arise that would make this program go wrong. And it's really hard to figure out where the bugs are in a piece of code like this. Now just imagine that you had not one interrupt, but 10 possible interrupts, you have priorities amongst them, and your code runs into thousands of lines. Right? For embedded code, that's about what you would see. And now you have to think about all the possible cases where an interrupt can occur infinitely often and your main code will not make progress. Or you can have a situation where you have a deadlock because you didn't set the priorities right or something like that. So you have all these possibilities, and it gets really hard for us humans to think about where the bugs are. But luckily what we have is a whole bunch of tools that will help us find these bugs easily and write correct code. And these tools at the heart, at the core, are based on finite state machine modeling and automatic ways to traverse edges on the state machines for the ISR and the main thread in a way that all possibilities are explored. And if there are bugs, you get a possible input conditions under which those bugs get triggered. You get an error trace, and you know how the system went wrong. Okay, so what we're going to do in the next 3 lectures is go back to the Mittelman state machine, and what we're going to work towards is Maybe next week we'll come back to this code and we'll see how we can model this code with state machines and how the state machine model helps us find all the bugs we discussed today. Okay? Are there any questions? All right, so see you on Thursday.